classes, we are going to learn about fluids under deformation. For example, let us pick the sea wave breaking. Maybe if you are really near the beach, it will be very massive kind of scales and so on. Mathematically, if I would like to really describe, what we do is we take something like a point within that fluid, zoom that fluid, whatever that point, then it looks like a Cartesian framework. On Cartesian framework, it looks like a box. If it is cylindrical kind of system, it will be cylindrical infinitesimal element. So pick that. Try to look at, in fluid mechanics, we always try to talk in terms of stresses rather than forces. Forces are equivalent of stresses. If you are going to suitably multiply with areas, add them up and so on, you will get effective forces. Because of that, it might get accelerated, it might rotate, torques will be generated and so on. The basic nature is stresses will be the basic thing. On surfaces, they will act. Suitably, they add it up to create such kind of effective forces. This is the fundamental basis. And here, what we are trying to really look at is, maybe pick any of the surface, try to write down stress components on the surfaces. The first one, subscript, always be normal direction of the area. And the second subscript, always be, or superscript, always be the force direction. That means if there is a force normal to that plane and the plane normal also in that direction, we will call sigma xx. So only that kind of force for that area gives me that stress component normal to that. Similarly, forces can be acting parallel to the surface also. So the surface normal is in the x direction, so x direction. In case if there is a force acting on the surface, to describe that kind of stress component, we will call sigma x comma y. Y is direction of the force. So the coordinate system is, this is z, x direction, y direction. So on that surface, in case if I have sigma xy stress, basically it can be decomposed into some force acting parallel to that surface in the y direction, and the surface direction is normal to that plane. That is what we call sigma xy. Similarly, sigma xz component, this one, corresponds to a force acting parallel to that surface in the z direction, and surface is x direction. That is the way we describe. Similarly, on the top side of the surface, let us pick this surface. Any stress component sigma yx corresponds to y directional plane and force acts in the x direction. This is the standard convention. Similarly, the force normal to that surface we will represent by sigma yy. Similarly, sigma yz means the normal direction of the surface is y and force might be acting in z direction, so that I can represent by a stress component sigma yz. Similarly, we have this purple surface. The normal is z direction, so z, z, z. The force which is acting in the direction of x is x. Force acting in y direction is y. Z direction is z. That is the way we represent these stresses. The frontal side surfaces I am showing. On the backward also, you will, backside surfaces also, you will have similar kind of forces or stress component. All these things together acting so that the material either under equilibrium or accelerating or rotating. In case the frontal ones exceed the backside ones, then immediately material start accelerating in that direction. Now frontal surfaces is subjected to more shear compared to backward surfaces. Then the objects start rotating. So whatever the things you are learning in dynamics, something like angular momentum conserves, forces, F is equal to ma, torques and so on, so things, these are very easy to handle like dynamics. But actual contribution comes from the material, because material subjected to these stresses, the resultant of all these stresses on particular areas leads to that effective torque. Saying something like my torque acting on a material is so and so thing, so it is trying to spin, is easy to say. But actually on material, these stresses, the shear stresses on the surfaces acting such that you will be in a position to spin. Maybe take your pen. You might think that if pen is rotating, there must be equal opposite kind of forces on the ends so that it is creating a torque. The way how you apply is you take your palm, keep pen in between your palms, and you move your hands in opposite directions so that pen start rotating and also translating. That is actually distributed on the material. You don't apply force. All the palm applies or creates some surface contact with the material so that it will be distributed on the material. Effectively, that's going to create torque on the object. That is the way we quantify it in fluid mechanics. And this tiny element, it can be for the sea breeze, it can be even for the rocket exhaust. So naturally, the question comes, how much stress acts on these materials? Maybe that infinitesimal. If I know that intricate blocks, each individual is more like, you can think of it in this way, like atomic kind of description. Talking something like a cup, pen, paper, all these things are beautiful. These are the products. But the essential building blocks might be atoms, maybe subatomic particles, maybe further subatomic kind of things. In the same way, the material description, the kind of rotations, translation, all these things, usually we connect with stresses, strains at that smallest scales. These scales much bigger than molecular scales. And especially what people have found out, if something like you identify a tiny infinitesimal element like material, usually in terms of strains, the deformations, people try to observe that it might completely elongate, it might be completely get compressed, or it might be get rotated, it might be get sheared. These are the essential building blocks through which you can really describe any object which is under deformation. Elongation means you are going to stretch it. You might be going to stretch it in X direction, in Y direction, Z direction, it can be. You can reverse the process. You call compress. So the material element completely squeezed. You can rotate it. You can apply forces on the lateral direction so that it might be subjected to shear. If you know these four components like elongation, rotation, shear, and compression, you can describe any of these material properties, bring constitutive equation even to model stress. And that is the place where we are heading. The first step is trying to understand what it means strain. If I understand strain, then I can connect with stress. Think of a situation. I'm giving you a plastic pen and also I'm giving you a rubber band, asking you to apply deformation. Though you might be applying the same forces on the two material, they will have different deformation. Because of that, the internal stresses generated in the material also different. So let us look at the first step. The very first essential quantity important is linear deformation. The second thing is angular deformation. Linear deformation means basically how volumes really change. Angular deformation is something to deal with rotation or shear. So volume changes means it might be elongating or compression. Angular rotation or shear deformation is you have an object, initially it might be rectangle. You apply forces on top and bottom so that it try to deform into this particular shape. This is what we call shear deformation. It is at infinitesimal level we are trying to talk about. The similar kind of forces you are applying even on the other surfaces. Then the object, instead of getting sheared, what it start doing is it starts spinning in this way. So we always talk in terms of stresses by taking care of areas, no more forces. So on this surface, I have applied one particular stress component. Here also another stress component, here also stress component, here also stress component. Then material starts spinning. Instead of that, you didn't apply those shear stress components on these sides. Then material really gets elongated. That one has to distinguish. And why we are talking about all these things is in 16th, 17th centuries, people try to understand what it means viscosity. For that purpose, what they try to do is they take something like two parallel plates. So you have a glass plate, another glass plate, liquid is there in between them, or you dip two plates in between the liquid so that the blue color portion is liquid, and fix the bottom side plate. This plate, try to fix it and only try to shear the top plate. Observe what kind of fluid motions one will see. What people have observed is there will be very high velocity near the plate side and very low velocity on the fixed plate side. And further, what they have observed is the fluid in contact with the plates always acquires its velocity. That means a moving plate, the fluid layer which is in contact with that moving plate acquires moving plate velocity, and the fluid layer which is in contact with a fixed plate always acquires fixed velocity. That means zero velocity. And what further people have observed, it changes as you go down into the plate. That means even though you are applying shear on the top side of the liquid, something like that momentum all the way get transported downward direction. The momentum what you are applying is in the x direction. This is x direction. If I am looking at coordinates, this is x direction and this is y direction. You are trying to move the plate in the upward, I mean on the top side of the liquid layer in the x direction. That means you are applying momentum only on the plate. But somehow surprisingly, what people have observed, all the liquid layers down also start acquiring something like momentum, which is a bit counterintuitive to them in 16th and 17th century. Think of a situation, there is no air in space, something like you try to move a plate and expecting some other planet also start moving in that direction, in that particular vacuum. Here, when you are trying to move a plate on the liquid, all the liquid layers which are in contact with each other, you can think of something like it's a stack. Paper stacks, first stack, second one, third one, fourth one, fifth, sixth, seventh, eighth, and so on, so kind of thing. You try to move the top one. All these layers start moving in this direction. That has really surprised them. Why? We might think that it is very obvious question. If I am trying to apply the top one, the bottom one also in contact with each other, so they are trying to move in the same direction. But the question, what they try to ask themselves is, if I am trying to move, all the layers could have moved with the same kind of momentum down, but that's not happened. You take initially a bunch, this is the stack. If I apply force on that, this entire thing could have translated to new location, but that didn't happen. Top layer could have really moved. Again, take this stack, apply this force on the top, stress, at that time they didn't know, only the top layer could have displayed, but instead of that, all these layers start moving. If that is happening, definitely it's a surprise to them, especially in 16th, 17th century, when naturally science is picking up. If that is happening, the first observation, what they called is, somehow fluid has a magical healing power to sense momentum, to transport from higher layers to lower layers, or from one layer to other layer. And the momentum transport happened in a linear way. In that sense, you pick the top layer, it has the particular momentum what you are trying to apply with hands, but that gradually decreases linearly. This is the second observation what they have figured out. That was really intriguing them. Then they try to really understand, okay, why I should really take something like parallel plates. Let me pick something like 2 cylinders. Fill liquid inside that. 2 cylinders means these are something like a drum, opened on both sides. One more cylinder, keep it, that's also opened on the other sides. In between them, fill liquid. Now try to spin either outer one or inside one. What they observed is, when they pivoted, so let me use a red color, fix it on a bearing. That means it's more like you take your pen, maybe make holes on the ends of that pen, try to suspend that on a wire frame, something like a ring. This is what you call bearing. You are just going to suspend it. And over that, you have another one. That's also suspended. More like telescopic kind of arrangement. Put liquid inside that. Everything suspended in liquid, maybe you can think of it. Now try to rotate the outer one, or maybe try to rotate the inner one. When that is happening, when it is in contact with the liquid, if you rotate the inner one, outer one also starts spinning. When you are spinning the outer one, inside one also starts spinning. That also really surprised them. How liquid is having that magical power to transmit this momentum, the angular momentum, from inside to outside or outside to inside. We can always easily talk about, no, fluid is in contact, that is the reason it is trying to spin. That is more like a hand waving argument, or it becomes more like a magic. Something you put liquid, so when you are spinning, the other one also starts spinning. But the same thing, they didn't really observe it so easily when they fill it with air. When you start spinning, outside one, air is there. Inside one is not having that surprisingly the similar spinning rate what liquid water is doing. Then they try to put oil. Then they try to put mercury. Then they try to vary the fluids. In fact, they try to put even sand grains. Surprisingly, each of these material have different kind of magical rate of spinning, these inside to outside or outside to inside. Then they start calling like, oh, there must be something named transport property associated with these fluids. The magic is transport property. It depends on which material it happens. If that is the case, let us call that one as dynamic viscosity. Is the essential fluid property which can transport momentum from one layer to the last layer of that liquid. When one of the layer is moving, other layer also start getting that transport, momentum transport. Not only that, it transport thermal energy, it transports linear momentum, it transport angular momentum, conductivity, and so on, so kind of thing. So materials possess something named these transport properties. This is the magical property what they figured out. Then they try to ask themselves, okay, I have very different kind of fluids inside the system. I might be getting different kind of transport rates. It becomes more like a hand waving, or perhaps maybe more like a dictionary English linguistic kind of level. This is having high, that is having high. Can I quantify it? Further purpose, what they try to do is, if I would like to quantify, I need to really bring something named mass. how much force I have applied, how much momentum transport happened, in some sense connect it. So for that purpose, what they try to do is measure the velocity profile across the layers, from one layer to other layer, how that layer is moving, what is the velocity, measure it, measure this velocity, measure this velocity, measure this velocity, measure this velocity. Maybe what I mean is, you pick the stack, these things will be getting displaced from one location to other location. That is the way you measure this velocity. All the layers which are in contact with walls always stuck to there, and which we will call no slip condition. If wall is moving with a velocity, the liquid layer in contact with that moves with the same velocity. If wall is at rest, liquid layer also at rest. That is in principle what we call no slip condition, and layer by layer deformation happen. Now what they did was, let me quantify those kind of things. I apply something named on the material, how much force or stress component per unit area I'm applying, how much deformation it is happening, record them. Or how much deformation is happening and what is the connection with stress, shear stress, because you are trying to shear them, record them. If they or if one start recording them, let me use some other color. For liquid water, they observe a straight line relation. That means you measure the components, you apply very little shear stress, how much deformation? Increase the shear stress, how much deformation? Increase the shear stress, how much deformation? How do you apply? Maybe the easiest way is, you take liquid block, keep a plate, connect a pulley, maybe connect a rope, hang a weight. And this plate is very long. So you are subjecting something like a force, and you know how much surface it is in contact with that. This is the plate, like a conveyor belt you can really think of. You connect something like a rope, hang a weight. So you know how much force you are applying, on which surface it is acting. So one can always calculate what is the sigma, because y is the direction, normal surface, and the x directional force is x. So sigma yx, one can really calculate. And you observe by keeping dies, red color die, from where to where it really went. So one can always calculate what is the deformation, or more precisely deformation rate per second, how much it is getting deformed. That we can really track it. And what they figured out, maybe oils, liquid water, all these things showed very straight line relationship. Can you see the curve? Hello?
Yes, sir.
Wonderful. But when they have put honey, they try to see deviation from this straight line. When they put glycerin, they try to observe again straight line. They try to put something named thixotropic fluids, maybe melting some of the materials like plastics, try to put there. They observe different kind of materials. They put glass beads inside the liquid water. They try to make clay suspensions like mud water, stake it, try to apply it. It is not straight relation they try to observe. It is somewhat different. And that kind of fluids, what they try to call is non-Newtonian fluids. And they try to call Newtonian fluids where your shear stress proportional to deformation rate. If that is happening, they try to say that Newton's viscosity law applicable. We don't know whether it is proposed by Newton or not, but we call Newton viscosity law where stress proportional to strain rate or deformation rate. Deformation means you apply velocity u here. This is zero velocity and this is a y direction. So how du by dy or del u by del y varies in the upward direction. You measure it and call that one as deformation rate. Units are meter per second by meter 1/second. It's more like your Hooke's law, stress proportional to strain. But in fluids, whenever stresses are applied, they always be subjected to continuous deformation. So it's not appropriate to talk in terms of deformation or strain, but it is appropriate to talk per unit second or per unit time how much deformation has happened. So that's the thing what they try to call as deformation rate or strain rate. And what they figured out, only certain fluids where applied shear stress proportional to applied strain rate or deformation rate. Applied means we have seen that you take a block, you connect by a pulley, you hang a weight. So you know what is the shear stress acting and you know how much deformation rate is happening del u by del y. If shear stress proportional to your deformation rate, then call that proportionality constant as dynamic viscosity. And this is a specialized fluid property which can transport momentum from one location to another location. Air has its own kind of transport property which is very low dynamic viscosity, and water has very high dynamic viscosity, and so on, so kind of stuff. And based on those materials, they try to quantify it. Is that clear? Hello?
Yes, sir. Yes.
And that had a very big significance in terms of industrial revolution, especially in the process plants. How to transport coal, how to really crush coal, how to pulverize that, how to really extract thermal energy, how to run steam turbines, whether you would like to really boil that and do that, or whether you want to transport it, whether you want to participate in combustion of certain process, or perhaps how to wash the things, how to clean the things, how to use it for steel industry. These kind of very essential things over the time picked up to really do very big engineering. If you are really seeing, before 17th 18th century, industrial revolution was not that great. I'm not getting into the details like whether it is good bad for the society and so on, so kind of stuff, but this is the way it happened. Only in the 18th century onwards, it's not just money can buy you everything and anything. It is more than that. So people in the 16th century, 15th century, 17th century worked really, really hard to really discover these kind of things. That ultimately led to this business capitalistic environment to create such kind of massive industrial revolutions. Today, if you are seeing something like, oh, this is the way I need to paint, this is the way I stick, this is the way I have to really make coatings, this is the way I want to really wash my clothes, this is the way I want to really create spinning, this is the way I want to really put color prints, is not that obvious during that 16th, 17th century. And people try to discover these kind of fundamental steps step by step. And you should really look at, there is a Nobel Prize winner named Edward Teller. Slight digression. He's a Nobel Prize winner, physics. He always supposed something like today's science is tomorrow's technology. And that is the way the 16th, 17th, 18th century guys really went ahead to bring that revolution in the 19th century. You require money all the time. There is no doubt about that. But it's more than that. Any product development is more than that. And they start calling, like characterizing, like, okay, if this is kind of oils, you will have this kind of diluent behavior. If it is something like this, you will have some pseudoplastic nature. Unless you apply minimum stress, you won't really begin something like deformation. Call it like Bingham plastics and so on. Why I'm saying is this important. For example, you want to really work on medical devices. Let us assume it. You want to really filter out blood. Filter out blood for what purpose? Maybe you want to really help society in terms of faster cleaning of blood. Maybe in terms of contaminations. Maybe you want to enrich oxygen. Maybe you want to really take out your carbon dioxide. Maybe you want to separate out plasma. Maybe you want to really purify urine. That is another big problem for most of our elders, like kidney dialysis. It looks like, oh, no, man, I don't want to really touch this kind of thing. These are yucky kind of thing. But those are the things which really tremendously benefit society. One of the component, I'm not saying only rocket planes and so on, so kind of thing. These are also have a bigger impact on society. Unless you really understand what kind of material it is going to do, how do you even construct something like rotating parts to separate out these filtration things? How do you enforce that red blood cells won't get squashed but purified? You require to understand this material properties. Under what circumstances they will be crushed. Once they are crushed, they are dead, the cells. You cannot really so easily construct it unless bone marrow again construct those red blood cells. But now any mechanical equipment where you would like to really purify the things without understanding this kind of momentum transport issues, how will you be in a position to make sure that these are stress limits are good enough to transport it nicely? You don't begin something like you straight away construct machine. You do something like a background work. What are these stresses? What are the things? How much deformation happens? Is it permissible limits or not? And so on, so kind of stuff. That is the way it works. Okay. So one of the important component, what they try to figure it out is this Newton law of viscosity. Trying to understand shear stress proportional to shear strain rate. Your blood doesn't follow that. It's a non-Newtonian thing. It's a colloidal solution. Your milk, the daily consuming milk also doesn't follow that. That is the way they try to really discover there is something named viscosity of the system. Shear stress by shear strain rate, if you can really measure these two quantities, you can quantify it as viscosity. The present day's understanding of viscosity is completely different from 17th century viscosity. Present day's viscosity is because of molecular motions, how they really tangled, cohesive forces acts and so on, so kind of stuff. But during that 17th century, macroscopic information, this is what we call macroscopic. You pick engineering device, try to measure the things, then you will call macroscopic. You bring molecular motions, try to understand those dynamics by simulations, then you will call microscopic. And this kind of simulations are called molecular dynamics. For example, if someone would like to really improvise battery performance, that is the most recent topic, what people are looking for, energy security. You can generate a lot of energy from renewable sources, but where are you going to store it? What are the ways? Maybe earlier people used to think like cadmium kind of things and lithium ion kind of thing. Now recently what people are started trying to look at is maybe vast resources, we have something in terms of sand grains. They have higher specific heat, they have higher viscosity coefficients. So maybe all your solar energy store it in terms of sand grains. Isolate the system. So they grab the energy whenever you want to really discharge it, you bring something named heat exchangers and transport it. That means you can use entire Thar desert in a proper isolated way to store energy. And at underground levels, you can really construct something like heat exchangers, bring these heat exchangers contact with the sand grains which are isolated so that you can extract power. That is the way you can store massive amount of energy, maybe oceans. You can really take all this solar energy, carefully store it, or maybe enter your carbon dioxide dump into porous materials. When these gases, carbon dioxide really comes out of it, you construct this turbine blades which really impacts that to create energy. That is the way people start looking at variety of technologies to buy based on understanding of the basic concepts. Okay, any new invention requires such kind of understanding about fundamental properties, and that is the thing what we are trying to look at. The very first thing what we are trying to look at is this viscosity has a major role in terms of creating deformations. And the first deformation what we are trying to learn is something named linear deformation. Let us take an infinitesimal cuboid. Maybe your sea wave is breaking. You have picked a tiny particle and try to visualize that. That is the thing what we are trying to do. Now, in fluid mechanics, you always have motions. That means one side of the part moves with one velocity, other side of the part moves with other velocity. You can think of a rubber band. You apply one kind of force on one direction, other kind of force on other direction. Overall material moves, translates, and also gets elongated. Think of a situation, maybe take your kerchief, napkin, hold it on one side, apply force on the other side, it gets stretched. Same thing, one can do it on both sides. To mathematically quantify, what we are trying to say that is, maybe this entire side moves with one particular velocity u. Other one moves with other velocity. It can happen even on the other sides. But as of now, for simplification, we are going to pick only two sides. Now, let us fix something in coordinate system. X-axis and this is y-axis. With respect to that, if I'm going to really look at, this is y-axis direction, this is x-axis direction. And this material have coordinates like A, something named B, I'm going to track it because this position is at x location and this position is x plus dx. This is the way I'm going to really define. The surface is from reference coordinates I'm going to measure, which is at x location. Other one is other infinitesimal element is at x plus delta x location. And both the sides are subjected to velocity, maybe equal, maybe unequal also. If it is equal, it just get translated. If it is opposite and equal, it will be really squeezed. If there is a variation, it will be get translated and also get elongated. That kind of configuration I would like to really look at. And especially at fluid mechanics and field, Eulerian fields, the way we describe is velocity at a location x, velocity at a location x plus delta x connected by Taylor series. And this surface is moving with u velocity within a short span of time delta t. This entire red line moved to a black line because the entire thing, this moves with you, this moves with you, moves with you, and so on. That covers a distance u delta t within a short span of time delta t. Similarly, this surface moves with a velocity u measured at x plus delta x in a short span of time delta t. So it moves by a distance u at x plus delta x multiplied by delta t. Now I would like to really ask myself, how much overall elongation for this material happened? So the fluid element in between x and x plus delta x position, how much elongation happened? That if I would like to really do, u at x plus delta x multiplied by delta t minus u at x delta t. If I do Taylor series expansion, u at x plus delta x is u of x del u by del x delta x plus higher order terms, because this kind of mechanics what we call linear theory. Taylor series approximation holds for many terms. For example, if I want to really get 5, I need to expand around 4.9 to say that 4.9 plus 0.11 minus 0.01 plus 0.25 by 100 plus and so on, so kind of terms. But 5 can be effectively captured by first 1 or 2 terms. And that is the thing what we do for Taylor series. So u of x plus delta x is u at x plus del u by del x delta x plus any rest of the terms, what we call higher order terms in mass. The symbol what we use is O, big O of delta x square, because the next following order goes delta x square. This is the standard convention what we use. Now, if I would like to really have how much expansion happened in between these two surfaces, what I am supposed to do? Subtract ux plus delta x delta t minus ux delta t, which gives me del u by del x multiplied by delta x multiplied by delta t plus order of delta x square delta t. This is the way it has to be. Okay. Any confusion till this part? Hello?
No.
Guys, no. Okay, fine.
No, sir.
No, sir.
Now, because we know what is the change in length of the surfaces, though it is something like surface to surface, there is an extension. I'm going to measure in terms of length. So how much this block really turns out to be? So this one, we already know length is delta x, x and x plus delta x. Now, how much change in length is del u by del x multiplied by delta x multiplied by delta t. This is the change in length. Change in length. So basically, this plus delta x is total length of the system. And that's the thing what we would like to really quantify. So the change in length is del u by del x multiplied by delta x delta t by original length is x plus delta x minus x. And per unit time, I would like to really quantify. So by delta t. So del u by del x is change in length by original length per unit time. And the units are 1/2. And that what we have measured in the x direction. And the variable to really represent that we call strain rate rather than strain. Per unit time we talk. In solid mechanics, you talk in terms of strain. In fluid mechanics, you call strain rate. And that linear deformation is epsilon xx. You denote it del u by del x. Just a notation. Similarly, if I do the similar process in the y direction, the velocity with which these things are moving is at v of y. And this surface goes at v at y plus delta y. That means the change in length is per unit time del v by del y is the strain rate in y direction. Similarly, in the z direction also I can really do. This is the z directional. This is W at z plus delta z is the velocity with which it moves. The back one is moves with the W. So the strain rate in the W direction is epsilon zz del W by del z. Sometimes we use superscript, sometimes we use subscript, but the meaning is surface and force directions. We have to really be careful. That is the only thing. Great. And this kind of strains, these are called strain rates, going to elongate volumes. Together, if they are acting, they might elongate, explode the volume, or they might compress the volumes. So they differ volumetrically. We calculated only volumetric strain rates. And typically, the forces which try to do that kind of volumetric, we in some sense associate with the pressures. When we are going to learn little bit about hydrostatics, we will be in a position to really appreciate such kind of expansion compressions are so easily possible by these pressure terms, the stresses. So something like strains, what we are trying to see is compressions uniformly equal in all direction, we will call pressure. But unequal kind of compression, unequal kind of expansion can also happen volumetrically. Then we will call that one as shear strains. Shear is the one which can also lead to that. Not only deformations, but unequal kind of distribution of these velocities on the top side, front side, back side can really stretch these materials unequally in the directions. Just 4 more minutes, we are done. Now, let us ask, initially I have a material of delta X, delta Y, delta Z size. Delta X, delta Y, delta Z. Because of these unequal U's, V's and W's, how much expansion happened? Can I really quantify that volumetric expansion? For that purpose, what we are trying to track is in the direction, how much change in length happened and what is the total length. Make a table. In X direction, if U components are the ones which are creating the strain, then the change in length is del U by del X, delta X multiplied by delta T in time delta T. So the total length is delta X plus del U by del X multiplied by delta X delta T. Similarly, in the Y direction, yeah, you guys, whoever so would like to leave, perfectly fine. I just want to close this and leave. Similarly, in Y direction, the change in length is delta Y, delta T multiplied by del V by del Y. So the total change in length is delta Y initially plus del V by del Y multiplied by delta Y delta T. Similarly, in the Z direction, the change in length is del W by del Z, delta Z, delta T. And change in length plus original length, this is the original length plus change in length. So that is the total length. Once we know the total length, we can always calculate what is the final volume. Total length multiplied by total length multiplied by total length. That is the thing what we are trying to do. Total length in X multiplied by total length in Y multiplied by total length in Z. If I do that, simplify by pulling out delta X outside, delta Y outside, delta Z. So delta X, delta Y, delta Z multiplied by 1 plus del U by del X delta T, 1 plus del V by del Y delta T, 1 plus del W by delta T. So what we have achieved is, now I can always construct something named volumetric strain rate. How much volume change to original volume? That is the thing what we call volumetric strain rate. So already we know total volume. Change in volume means subtract delta X, delta Y, delta Z from total by your total volume multiplied by time delta T per unit time. If you do that, you will be in a position to really call volumetric strain rate. And that volumetric strain rate del U by del X, del V by del Y plus del U by del Z plus higher order terms, because delta X, delta Y, delta Z cancelled out. You will be in a position to divide with the delta T. So the very first terms what you are going to get is del U by del X plus del V by del Y plus del W by del Z plus any products, which we can simply write it as divergence of velocity field. So the whole exercise what we have tried to achieve is, whenever this kind of velocity is unequal happening, the overall change in volumetric strain rate proportional to your divergence in velocity del dot Q. And in tomorrow's class, we will see about this angular deformation rate. Okay. Sir, meanwhile, you guys can begin and I will join in 5 minutes, sir. My class is about to end. Thanks. So in tomorrow's class, we will learn about, instead of volumetric strains, what it means angular strains and how to connect that and so on, so kind of stuff. Okay. If no queries, we can close this session. Any queries in today's lecture?
Yes, sir. Sir, what did you tell about the preserved shape part? Like
Okay.
all the XYZ direction, they need to be equal. They need to have equal.
If they are equal, they will be achieved only by your pressure terms.